In this video, we are going to learn one of the very important technique called the comparison test. So, comparison test. So there are two comparison tests, what we call the direct comparison test and the limit comparison test. So we have two tests. One is called the direct comparison test, direct comparison test. That sometimes we call the DCT, and then we also have the most important one, what we call the limit comparison test. Limit comparison test. So this is what we call the LCT. So we have direct comparison test and the limit comparison test. So any problem that you can do from direct comparison test can also be done using limit comparison test. But there are certain problems that you cannot use the direct comparison test, but you can still use the limit comparison test to prove. So according to that argument, the limit comparison is more important, because this is much more advanced and there are a lot of things that you can do with that. Okay, so before we go to the actual theorem, I would like to remind one of the results that is really important when you do these two tests, that what we call the P-integral test. P-integral test. We can say P-series test, not the integral test. So let's go with the P-series test, because the P-integral test is coming from the P-series test. So it's a P-series test. P-series test. So what's a P-series test? So it says that the series, so sigma n going from, you can start any number, but I just put 1 here. 1 over n to the p has two results. It's gonna converge if p greater than 1. It's gonna diverge. It's gonna diverge if p less than or equal to 1. So this is what we call the P-series test. This is a very powerful result, and we can use this a lot in this section. So let's go to the actual result. So we are not going to prove it, but I'm going to give the result here, and then we're going to do a lot of examples. So the theorem is what we call the direct comparison test. So direct comparison test, or what we call the DCT. So what is that? So there are, what we can do, we can compare two series. And the convergence of one of the series we already know. So we can compare the series, the convergence of which we already know. So the result says, so let sigma an and sigma bn be two series with terms which are, we assume that are not negative, with all the terms either 0 or positive to avoid confusions. Okay? For some n after a n. Okay, so at the beginning we don't worry about what's going to happen at the beginning, but after some n, everything should be either positive or should follow this special relationship. This what's the relationship? The terms of the Bn series has to be larger than the terms of the An series. And what this means? This means that after some n, so we don't need that to be true for any n. So after some n, this should be the case. So you can start with any number. So there are two results. So what it says that, so we know this relation works. So it says that the first one is, we know that the larger series sigma bn converges, then if the larger series converges, then the smaller series has to converge. So this is the obvious result. Why? But it says that the larger one has a finite sum. When you add it, you get a finite number. So then it automatically says that the smaller one also should have a finite sum because it's smaller. Okay, smaller. And we assume that these terms are not negative, so that we don't worry about going to the negative infinity. Okay, number 2. Now, if the smaller one diverges, so when sigma n is smaller one diverges, then automatically the larger one has diverged because that's bigger diverge. So yeah, so this is what we call the direct comparison test. It's a very powerful test, and you can see that. So what we have, you have two series. You can compare with one another, and the convergence of one series we know, and this can imply the convergence of the other one. So it's like that. So we assume that the terms gonna be a n less than or equal to b n. So that's the condition. And then in this case, if the larger one converge, the smaller one has to converge, and if the smaller one diverge, the larger one has to diverge. So remember the direction of this. So let's try to prove certain problem that we are having some trouble. So as the first example, we're gonna go to this one. So this example number 1. So test for convergence. So let's say test for convergence. For example, let's say this one, a sigma n going from 1 to infinity 1 over n squared plus 1. So if you look at this series, so what we're going to do, when you get a series, just think of only the largest term of the numerator and the denominator. That's kind of give you what you're going to compare with. So in this case, what you're going to do, you're going to compare this with, what do you do? If you ignore the plus 1 in the denominator, you have to compare this one with n going from 1 to infinity 1 over n squared, because you can ignore this 1 from the denominator, because we only worry about the largest term of the numerator and the largest term of the denominator, and then they simplify them. Okay, so that's the one we're going to compare. But what do you know about the second series? That's a p series, p equal 2, so that means it's going to converge because p is greater than 1, so it's converge. So that's convergent series. So only thing you need to prove that the corresponding terms are smaller. The n terms are comparable. So let's finish the rest of the argument. So you can see it's a very simple problem. So note that 1 over n squared plus 1 is less than or equal 1 squared. Why? When you add something to the numerator, when you add something to the denominator, it gets smaller. So that means when you add something to the denominator, it gets smaller. So that means the fraction on the left side is smaller. Okay, this is for all n greater than or equal 1. Okay, so that's true. But we know that the sigma 1 over n squared converges. We need to say that converges since it is a p series. It is a p series with p equal to, which is greater than 1. So by the p series test, we know that the second one converges. So that means the larger one going to converge. So the smaller one has to converge. So by the direct comparison test. That's the whole argument. You need to say what test. So by the direct comparison test, the other series n going from 1 to infinity n squared plus 1 converges. So this is how you make the complete argument for that. So you need to write what series you want to compare with, and then you want to show that the corresponding a n and b n terms behave the way we want, so that the a n is less than or equal to b n. So that's true. And then we know that one series can converge, so the larger one can converge, so the smaller one has to converge. So let's do another problem. So how about this one? So number B, sigma n going from 1 to infinity 5 over 5n minus 1. So if you look at this series, you need to think of just do a mental calculation to simplify it. So in the numerator you only see 5, so we leave it. in the bottom you see phi in minus 1. So what are you going to do? You can ignore minus 1, and after you remove minus 1 you're going to get phi over phi in. Phi over phi in, once you simplify, it is simply 1 over n. So that means you're going to compare with sigma n going from 1 to infinity 1 over n. Why 1 over n? Because you see that you're going to get phi over phi n. Once you cancel phi, it is 1 over n. So that's why you get 1 over n. So you compare 1 over n. But what do you know about 1 over n? 1 over is the harmonic series. That's we know diverge. Okay, or it is a p series p equal 1. So you can say 1 over n. It's a harmonic series gonna diverge. But what do you know about the relationship between the two? But we know that when you subtract something from the denominator, the term gets larger. So that means 1 on the left is larger as we expected. So note that phi over phi n minus 1 is greater than or equal 1 over n for, in this case, all n, for all n greater than or equal. As I told you, we don't need all. We need all, but we don't need 1. Okay? But sigma 1 over n diverges. This is what we call the harmonic series. Diverges since it is the harmonic series. So we know that harmonic series diverge. Or you can say, oh, this is the p series with p equal 1, which is less than or equal to 1. So we know that p series is going to diverge if p is less than or equal to 1. So you can see that the smaller one diverge. So the larger one has to diverge according to part B of the direct comparison test. So by the direct comparison test, the series, it's a good idea to write the series again. Phi over phi n minus 1 diverges. Okay, so you can see that it's not that bad. It's not like a very difficult argument. It's a very simple argument, but you need to make sure that you include all the parts. Now let's try to do this problem. So as for next one, part C, let's do this. Let's do sigma 1 over n minus 1, and you know that in this case you can put n equal 1, so I'm starting n equal 2 to infinity. What do you do if you ignore negative 1? You're going to compare this with, I'm going to say versus, you're going to compare this with 1 over n. So it's clear, n going from 2 to infinity. So this is still the harmonic series. Even if you ignore that first term, it doesn't matter, the convergence does not change. Even if you ignore any finite number of terms, you can ignore the first million terms, still the convergence is the convergence. You remove finite part, so you can remove finite part anytime. And then now what's going to happen? 1 over n minus 1, we know that you subtract something from the denominator, so it gets larger. So again, note that 1 over n minus 1 is greater than or equal 1 over n for n greater than or equal to but sigma 1 over n diverges since it is a p series with p equal 1, which is less than or equal to 1. So by the direct comparison test, sigma n going from 1 to infinity, phi over, not phi, it's a direct comparison test, that's the previous problem. direct comparison test, 1 over n minus 1 divergence. Good. So how about this one? Number D, sigma n going from 1 to infinity 1 over n plus 1. So as before, we're going to compare this with sigma n going from 1 to infinity 1 over n. But see that you are adding something to the denominator, so that in this case n plus 1 is smaller than 1 over n, but the larger series diverge. So the larger series diverge, but this side is smaller, so when the larger one diverge, you can't say anything about the smaller one. So that means the direct comparison test does not work here. So you can see, so DCT cannot, so can't work here. Okay? Because it's in the wrong direction. So this inequality is in the wrong direction. So that means you cannot use the direct comparison test to prove that, test the convergence of 1 over n plus 1, because the inequality is in the wrong direction. So that means we need to wait for the new test, the limit comparison test to do this. So that's why it's more powerful in this case. Okay, let's try to do one last problem before we go to the limit comparison test. So this is the last one of this section of this theorem, under this theorem. So let's test for n going from 1 to infinity ln n over n, ln n over n. So what we're gonna do for this one, so we have a log function. So that means we need to understand certain properties of the natural log. So what do you know about natural log? So let's look at the graph of the function. So the natural log function behaves like this. So it is, so it's going to go like that. That's 1. So at 1 it is 0. And then we know that number E is how much? It is 2.718 roughly. So it's approximately that. So that means like around 3. So we know that at that value, how much ln E? Ln E is exactly 1. So you get 1. That's exactly 1. So that means if you pick any number which is larger than 3, what we notice is the natural log function. The natural log function is bigger than 1 if n greater than 3 or equal to 3. N greater than or equal to 3, the natural log function is bigger than 1. And also we know another general result is a log function. This is a log function, and if you graph the y equal x, so you can see the y equal x is goes like that. It's a y equal x function. That's an n equal n function. So this is y equal x function. So that this says that the log function is below that function. That means, in other words, we have one more result. We know that the log n is always less than n, bigger than 1. So this is a interesting result. So this is for n greater than or equal to 3. So we ignore the first term. So please remember this result. This is a very important result that we can use. So we know that the log n is between 1 and n. It's always less than 1, is bigger than 1, less than n, bigger than 1 and less than n. So we can use that result here. So what we can do, we can replace this ln n by 1. If you do that, then what you can do, you're going to compare this with n going from 1 to infinity 1 over n. That's what we're going to compare with. Again, we can ignore the first two terms. So what's going to happen here? So we can just forget about the first two terms and we can start with n equal 3, and later we can add those two terms. So that's what we can normally do. Um, so so for example, in this problem we can actually we can start with 4 if you want, or we can still go with 1, but the argument doesn't change even if the first two terms does not agree with the rest of the term. So now what we know, so let's finish the argument. So so note that ln n is bigger than 1 for n greater than or equal to 3, and because of that, and ln n over n is less than or equal 1 over n. Why? If you replace the top by log, it is smaller because of our argument. We know that the log n is so log n is bigger than 1. So actually we write it that way. So log n is bigger than 1. So it's right. Is bigger than. So it's like that. So ln n over n is bigger than 1 over n, because when you replace ln n by 1, you see that it's smaller. Okay? For n greater than or equal to 3. So but the 1 over n diverges. So if you ignore the first two terms, so by the we simply gonna ignore the first two terms. So by the direct comparison test, so we know that the smaller one diverges, so the larger one has to diverge. So by the direct comparison test, the series we can now add the first two terms. That's why we write it starting with 1, so it doesn't matter. By direct comparison test, ln n diverges. Okay, diverges. So please try to remember this argument because it's a very powerful result. See how it works, and you need to know these graphs. So as an exercise, I'm going to ask you to try this problem. So try this. So what can you say about this series? N going from, I'm going to put 2 intentionally because ln 1 is 0, so you cannot. So I'm going to make it upside down. What's going to happen in this case? What do you think? Convert or diverge? So convert or diverge. So you can, if you want, you can say this as an exploratory problem. Okay, good. So those are the kind of problems that we are trying to do using direct comparison tests, just like some sample problems. So let's try to go to the more powerful result, what we call the limit comparison test. Because as I told you, we can do all the problems that we did using direct comparison under limit comparison. The test is much more powerful than this. So let's try to go over the result. So let's try the theorem. So this is what we call the limit comparison test. Limit comparison test. A limit comparison test, or what we call the LCT. Limit comparison test. We're going to compare limits. So how the theorem works? So suppose you again assume these terms are positive, just to avoid extra confusion, and Dn positive. We have two series which are positive, which have positive terms for all n after something. So we don't worry about what's happened at the beginning. Okay? After something. So this has 3 properties. The first one is the most important one. That's what we are going to focus on. So if the ratio, so what we can do now, we can take the ratio and take the limit. So we can divide by a and b and take the limit when n goes to infinity. Let's say you get a number. Okay, you get a number. anything other than 0. So you get a number which is not equal to 0. So then what's going to happen? Whatever happened to one series, the same thing will happen to the other series. So then uh, sigma an and sigma bn both converge or both diverge. So what it says that if the limit is a constant, whatever constant, it doesn't matter what the constant is, if the limit is a constant, we divide the two and take the limit. If the limit is a constant, it says that the two series behave exactly the same. If sigma a converge, sigma b n. If sigma a diverge, sigma b n diverge, because they just like kind of relate to each other by a constant results. So the both behave exactly the same. So that's the result. And then I'm going to give you two more results, like some other cases also. So if let's say we're going to get other limits. So limit n goes to infinity an over bn, but this is 0 now, equal 0. And we also know that bn converge. So if we know that the limit is 0 and also bn converge, that means an is comparatively smaller than bn. Okay, comparatively smaller than bn. That's what this limit 0 means. An is smaller compared to bn. But if we know that the series bn converge, since the values of an are smaller, it has to converge. So the limit is 0 and the sigma bn, converges, then sigma n converge. If sigma bn diverge, we can say it has to be only the converge. Now it's only for converge. Now the other case is infinity. So you're gonna get this to infinity if limit n goes to infinity an over bn equal infinity, and the sigma bn diverges. What does that mean? So an over bn infinity means an is comparatively larger than bn. That's what it means. But the bottom one is diverge. That means n is much bigger than that. That means sigma n also diverge. So we have those two additional results also. But what is more important is the first one. So if you get a constant, they exactly behave the same way. So as the very first example, remember we had a problem that we cannot do using the direct comparison. Now let's try to do this problem. So what was that? We're going to compare n going from 1 to infinity 1 over n plus 1. Because if you try to do a direct comparison, the inequality in the wrong direction, it's less than. But that's not what we exactly want. So what we're going to do, so we're going to compare this with, so versus what you do, you're going to ignore the 1 in the bottom, so you're going to compare this with n goes from 1 to infinity 1 over n. So in this case, so we have an equal 1 over n plus 1 and bn equal 1 over n. So what do you do? We take the limit n goes to infinity an over bn. It doesn't matter which one, but be careful. I want to enter theorem also, but I'm going to write a inside there. So it is limit n goes to infinity 1 over n plus 1 over n, and then this one you can write as limit n goes to infinity 1 over n plus 1. So division will become upside down like that. This is what you get, but n goes to infinity. When n goes to infinity, you can ignore the smaller terms, like you can ignore the plus 1, so it becomes n over n. So this is limit is 1. This is not equal to 0. That's a constant. So constant means the two series behave the same way. So that means, but we know that the second series diverge. So that means the first series has to diverge. So it's a constant. So the limit of the ratio is a constant. That means two series behave the same way, but one series diverge, so the other series has to diverge. but sigma n going from 1 to infinity 1 over divergence. That's a harmonic series. Diverges because p equal 1. So by the limit comparison test, the sigma n going from 1 to infinity 1 over n plus 1 diverge. You can see that you could not do this problem before using the direct comparison result, but using the limit comparison is a very simple problem. So you're going to compare with 1 over n. So let's do a few more examples. So how about this one? So let's say, for example, let's do a few more. The test for convergence. Just for convergence. Let's do 3 over 4 plus 5 over n plus 7 over 16 plus 9 over 25, like that. So if you get this one, let's try to write the n term. So sometimes you have to write the n term. So what happens? When n equal 1, you get 3. That means 3, 5, 7, 9. Those are odd numbers. So that means the top is simply 2n plus 1. That's how you write odd numbers. 2n plus 1 or 2n minus 1 depending on the situation. So here let's say 2n plus 1. What's the bottom? You can see the bottom is, you can see 4, 9, 16, 25. Those are squares. First one is squares of 2. Second one is squares of 3, squares of 4. That means that 2 squares means n plus 1 square. That's what. So that's the n term. That's the a. So if you simplify this, you can write this series as sigma n going from 1 to infinity. The top is 2n plus 1. It's a good idea to expand this. So it is n squared plus 2n plus 1. That is the expansion. So remember, when we have a plus b squared equal a squared plus 2ab plus b squared. So that's the expansion of that. So we use that and write it like this. So now we can do, so that's the series that we want to do. And then so you can see that now the question is, what are you going to compare this to? So what you normally do is you look at the largest term of the numerator and the largest term of the denominator and divide the two. So 2n over n square, so this is like 2 over n. So you automatically know the result. So 2 over n, that means the corresponding series sigma 2 over n does not diverge. 2 is just a number. Diverge, so this diverge. It's very simple. Okay, but let's try to write the let's try to finish the argument. So let's say, so you see, we know what your series is. Now let's finish the argument. So let's say compare with let's say sigma n going from 1 to infinity 2 over n. Now you know where the 2 over n coming from. If you're going to simplify, you only pick the largest terms and then simplify. That's going to be the series to compare. Okay, so we're going to compare with this one. Now you know that automatically you take the limit is 1 because you only pick the largest terms. It's always 1. It's one of the things that doesn't the book doesn't discuss that way, but this is much faster doing this way. So limit. So I'm going to call this is bn. So we have this is an. So limit n goes to infinity. A n over bn is automatically 1, but I'm just going to write it. Limit n goes to infinity. Here we have 2n plus 1. We can write this all of these things. 2n plus 1 over 2 over n. So this is the limit. N goes to infinity. We can write 2n plus 1. This is just algebra. N squared plus 2n plus 1 and make it upside down, that is like that. Since we only pick the largest term, we can ignore all those smaller terms, so we don't need any of these terms to make the argument, because this only works when n goes to infinity. When n goes to infinity, we can make this argument. We can ignore all the smallest terms, and you can see once you remove all the smallest terms, everything else get cancelled, and you get the limit as 1. So this simply becomes 1. It's always, because the way we do it is always 1. Is it not equal to 0? Okay, automatically. So that means we can say that the sigma n going from 1 to infinity 2 over n, 2 is just a constant, so we ignore that, diverges since p equal 1. Okay, we can still ignore any constant, positive, negative, anything. So p equal 1. So by the limit comparison test, sigma an converges. So you can see it's a very simple argument. Just imagine if you want to use a direct comparison for this problem. This can be very difficult. Very difficult. So I'm going to give you a problem for you to try. So it's similar, like this. This exercise. So do you want to try this one? Sigma n goes from 1 to infinity, 2n minus 1 over n squared minus 2n plus 7, something like that. Okay, so you can try this. You already know the answer, because if you look at the largest terms, you're going to get 2 over n. Then we diverge, so this diverge, we know that, but why don't we try and finish the rest of the argument? Okay, so that's the benefit of this, and you just need to look at only the largest term. Just look at the largest term. Good. That's about that. So let's do a few more different examples. So how about this one? Let's say 1 over 1, 1 over 3, 1 over 7, 1 over 15, like that. So what is this? You can see we have 1, 3, 7, 15. So what is the nth term? So this is like 2 minus 1, 4 minus 1, 8 minus 1, 16 minus 1. That means your series is 1 over 2 to the n minus 1. 1 over 2 to the n minus 1. N start with 1 to infinity. So that's a series. So what are you going to do? So if you ignore negative 1, you're going to compare this with 1 over 2 to the n. But we know this from the series lecture. This is a geometric series, because 1 over 2 to the n, you can write this as one as sigma 1 half to the n. You can see, so this is a geometric series. This is a geometric series with r equal 1 half, which is, so absolute value of r is less than 1, so converge. So this series converge. So, and then also you know that once you take the limit, it's automatically 1, so you can see that note that the limit n goes to infinity a n over b n. This is a n, and this is b n. A n or b n equal 1 automatically. So so this is going to convert. So by limit comparison test, sigma bn converge. So yeah, so you can see that, so you can do like 1,000 problems like this. It's a very simple argument. It's not that difficult. So let's try to do maybe just there's one more problem. Okay, so just one more problem. So how about, so remember again, only consider the largest terms. Okay, only consider the largest terms, and you can ignore everything else when you especially talking about the limit cases. So parts number C. How about this one? Sigma n to the cube minus n sine n squared plus 3 over n to the fifth plus 3 square root n plus cosine n going from 1 to infinity. Yep, you can see that this is really scary looking, but this is a very simple problem. The reason is we can notice few things. So note that the sine theta is always in between 1 and negative 1. So it doesn't matter what you're going to put in there, it's always between 1 and negative 1. Same thing. So cosine is always in between 1 and negative 1. So those two terms just between 1 and negative 1. So that means we can ignore, and then also square root n compared to other powers is smaller. So that means we can ignore pretty much all these terms. So you can ignore these, all of them you can ignore. So that means you're going to compare this series with n3 over n5. So that's what you're going to get. So n3 over n5 means 1 over n squared. So that's the series, but that's going to converge. The series converge. So this one converge. That's it. Okay. So very simple. So compare with sigma n going from 1 to infinity 1 over n squared. Okay. And the limit n goes to infinity a n over bn. So this is the a n series, this is the b n series, equal 1 automatically, because we leave the largest terms from the numerator denominator, which is always 1, which is not equal to 0. So by the limit comparison test, sigma bn, not b, a, sigma n converges. Okay, so you can see that it's a very powerful, very powerful technique. Just imagine for this problem, if you want to use a direct comparison test, this can be very difficult. Okay, so I will give you maybe 2 more problems for you to try. So these are like exercises, so why don't you try these? So exercise problems, so you're going to get, so I'm going to give you a series 1 plus 2 ln 2 over 9 plus 1 plus 3 ln 3 over 14 plus 1 plus 4 ln 4 over 21. Like, what can I say about this series? So you're going to figure out what the bottom looks like. The top is easy. Yeah, so I'm going to let you figure out that. And then I'm going to give like a little difficult problem. So these are like, extra case problems, because these are like little difficult. So how about ln n over n3 halves? Okay. So what can I say about this? And one last problem. So n going from 1 to infinity, we can say 3 n 5 half minus sine n over, we can say 2 into the, I'm going to say 4 plus 7n. So what can I say about this one? Great. So those results are important. So and also I'm going to give you a little kind of list. These are important. For example, this to remember. So we know a few things, like for example, so when we have uh, like a 2 to the n. So let's say not 2 to the n. I'm gonna write this one as, yeah, 2 to the n is it's always when we can say the first one is n is less than or equal any power to n. So if you have any number here, so this is always bigger than that. And then we have also, so the first one, and when we have a number like x is a number, x to the n, this is smaller than the factorial n. So for any x positive, it's always smaller, so that one is larger. And then the third one is we can say so like I just pick a number, so like 2 to the n. So and then so this is, we can say and factorial n is bigger than the 2 to the n, and this is bigger than n to the n. So this result is also important when you do direct comparison. So please remember this result. So n is smaller than 2 to the n, xn is less than or equal factorial n, and then 2n is less than or equal factorial n. So this is the last one is very important. So it has like several results in one. So this is very very useful when you want to prove certain results using the direct comparison. Okay, important for direct comparison test. Okay, so this is the end of the direct comparison test and the limit comparison test.